Hello everyone. Welcome to the next series of videos on Python code from scratch for regression analysis. I have already created a video series on multiple regression analysis using Python from scratch. If you haven't watched it yet, the link is available in the description below. In this series, we are going to discuss Python code from scratch for polynomial regression using gradient descent. Our objective throughout this series is to use gradient descent to fit a polynomial curve to the sinx function. The sinx function can be represented by an infinite polynomial called the Taylor series, which is given by sinx equals to x minus x cubed by 3 factorial plus x power 5 by 5 factorial and so on and so forth. If we observe this equation carefully, we can see that it is simply a polynomial with different powers of x. The coefficients of this polynomial are already known mathematically. In this series, instead of using these coefficients directly, we will use gradient descent to learn them automatically from data. As iterations progress, the learned coefficients should gradually approximate the coefficients of the Taylor series, allowing our polynomial to closely match the sinx. So before writing the complete implementation, let us generate the dataset that we are going to use throughout this series. Now to represent the sinx curve, let's range it from minus pi to pi, and let us have 2000 equally placed values of x. As you can see here, the x value ranged from minus pi to plus pi. Now for each of this value, we should calculate the corresponding y value as the sign of x. Now this gives us a perfectly smooth dataset where the relationship between the input and output is already known. Now, let's create another dataset by adding a very small amount of bias to the sinx values. This second dataset resembles real-world data more closely because practical measurements always contain a little bit of imperfection. Now let y be the sign of x plus random. Let's apply this to all the values of x. Now, throughout this series, we will use these datasets to evaluate how well polynomial regression can approximate to the underlying function. Now, let's go to our code and see if our program is running perfectly. Let's save these. This is the pure data. And this is the approximate real-world data. Let's copy the address. Paste it in the path and run it. Now, before understanding the complete Python implementation, let's first see what this program produces. The implementation generates the result in two different forms. The first output is a tabular format, where for every iteration we can observe the polynomial coefficients, the loss, and the gradient for the respective coefficients. This allows us to monitor how gradient descent updates the coefficients step by step. The second one is a graphical representation. Here, the original data points are plotted together with the polynomial predictions obtained after different iterations. As gradient descent progresses, we can clearly observe that the polynomial curve gradually approaches the original sinx function, which is represented as the blue line. In the tabular format, we can see that the bias coefficient almost leads to 0. The coefficient of x almost leads to 1, and the coefficient of x squared almost leads to 0, and the coefficient of x cubed, which is given by the Taylor series, is minus 1 by 6, which is approximately minus 0.16. And as we can see here, it almost reaches to that value. And after a number of iterations, we can see the loss has decreased as well. This shows that our gradient descent function is working well. Now let's implement this for the real world data as well. As we can see here in the tabular format, A leads to 0, the coefficient of bias. X coefficient is almost leading to 1. Coefficient of x squared, which should be 0, leads to 0. Coefficient of x cubed, which should lead to minus 0.16, leads to 0.16 negative. And the loss is almost 0. We can see here in the graphical representation, the actual data is the blue line. And after many iterations, the gradient descent is almost aligning to the real world data. This is it for this video. In the upcoming videos, we will build this entire implementation from scratch, understand every equation involved, and even develop a dynamic version of this code that can fit a polynomial of any degree without not manually changing the equations. Have a good day ahead.